Today, I would like to present a model for analyzing the effect of handoff control messages on the network capacity. Here is my presentation flow today. I will first talk about the motivations for this work. Next, I will talk about the system model which will be used to analyze the handoff control messages problems. Then, I will analyze how the control message will affect the delay performance of the other normal voice packets. And last, we will have some further discussions and insert conclusions. Since the handoff control messages share the same wireless channel with the voice packets, introductions of the handoff control message in the network will increase the workload of the channel. Usually, in order to achieve lower handoff latency, the handoff control message will have a higher priority than the other normal voice packet. So, the voice packets transmitted by the mobile stations may need to be delayed when handoff occurs. In order to improve the performance of the handoff control schemes, we can increase the amount of the handoff control messages. For examples, we can aggressively request the authentications and IP collection setups, or we can start the handoff process on a small received signal difference only. This increase in the handoff control message will affect those delay-sensitive applications like voice over IP. So we want to develop a performance model for investigating the effect of the handoff control message on the delay of the other normal voice packet transmissions. This model will be useful for optimizing the parameters in the handoff control scheme in order to maximize the system capacity and also the handoff successful probability. In the analysis, we will model the system as an MMPP-MMPP1 queuing system as seen by the voice packet. MMPP stands for Markov Modulated Person Process. In this case, that means the arrival events and the service time of the packet will be modeled by two separate Markov chains. For the arrival event, assume there are n identical and independent voice over IP traffic sources. Each of them will be modeled as a Markov chain with two states, on and off. When there are n sources, one of Professor Yu's paper have suggested that the combined arrival stream can be modeled simplest as n+1 state MMPP process. The state transition diagram of each of the sources is shown here. Voice packets will be generated at the on state, and the interpacket arrival times will be exponentially distributed. The mean interpacket arrival times will be 1 over lambda. When there is at the off state, there will be no voice packet generated. In our case, we can use this Markov chain to represent the overall packet arrival behavior. The number at each state represents the number of current active voice over IP traffic sources in the system. For example, suppose the current state is at 2. That means there are 2 active sources in the system. When one of them becomes inactive, the system state will change from state 2 to state 1. The rate for this change will be 2 out of, since there are 2 active sources and each of them will have out of to become inactive. Suppose the current system state is 2. There will be n-2 inactive voice over IP traffic sources. So when any of them become active, the system state will change from state 2 to state 3. And the transition rate will be n-2 times R on, since there are n-2 inactive sources, and each of them have R ons to become active.